let's start the actual stuff. Well, I'm not sure this is the actual stuff already, because this is about, it's a strange kind of topic, and I've never lectured on this, and I've been preparing until last night, 2 o'clock, so it might be a little bit chaotic, but hopefully it will be interesting in different ways. So I want to talk about 2 things in this kind of. Usually we immediately started with the technical talks, and we often got this feedback that people said, well, actually, it would have been good to start a little bit slower with something more general. So that's what we're trying now. And this more general thing has 2 parts. One is about some basic ideas of what machine learning inference generalization is about. This will be very informal and very light and nothing technical, so it will be easy to get in. And then the second part will be about some aspects of the history of our field. And our field is still pretty young, and maybe it's too early to write in history. And I'm not a historian, but I think there's still already some things to be learned from that. So let's start with these 2 things, and then the actual technical stuff will start after the coffee break. So the motivation, at least for me, for machine learning is adaptive behavior. So to do something successful in a complex environment, biological systems, animals, humans, have developed fairly advanced types of adaptive behavior through learning and evolution. And let me just show you a few examples of what kind of behavior I have in mind. So for instance, this one here is well, maybe let me stop this one. This is some kind of, I think it's a white blood cell chasing a parasite through the bloodstream. This is something that's going on as we speak in your blood, and it's already fairly sophisticated. And this one over here is a frog trying to catch a fly, which is quite beautiful. And even though it doesn't work in this case, even though it doesn't work, we're still far away from building or learning this kind of control systems. And here are some examples of what humans can do. So they can walk on water and all sorts of other interesting things. Let's watch a few. So this is a video that collects a number of other things, and you can find it on YouTube if you search for "People Are Awesome." So this is something called parkour. I think you probably know this much better than I do. It's basically about how to get fast from A to B. All right, and now the last one. So this all involved one person. There's also a very sophisticated collective behaviors. Now, I forgot to link this up to the speakers. Next room, yeah, can you hear it? So it doesn't matter the sound, but it's an amazing type of behavior, of course, that we have learned through culture, evolution, individual learning, etc. And there's this story about this specific cantata, which is that Mozart heard this when he was visiting Leipzig, where Bach was working, and he saw a production of this and he really liked it, and he wanted to get hold of the score, but nobody could give it to him, so he sat down, but it's probably not true, but it's a nice story. He sat down in a pub and he wrote it down from memory, and this has 8 voices and it's 15 minutes long. So it's very amazing what humans can do, what kind of behaviors we can produce, and we have no idea how it really works. So how can we understand this kind of behavior? Well, so this is a blackboard picture, very similar to our blackboard, apparently taken after Richard Feynman's death. This was his blackboard when he died, at least if the information in the internet is correct. And up there he writes something that has been quoted a lot, which is, "What I cannot create, I do not understand." So especially people, in a sense, there's some kind of motto for if you work in robotics. So robotics, you try to create a certain synthetic system, and hopefully you will also understand natural systems along the way. And this is one interpretation of what Feynman was saying. Of course, one can also interpret it differently, and maybe as a theoretical physicist one would interpret it differently, just more in the sense of what's written just below here, know how to solve every problem that has been solved. So try to understand things not by just reading a theorem and memorizing the conditions and the conclusions, but try to understand it by being able to reproduce the proof of it. So going into the real details of how the knowledge is built from each other. And of course, that's also something that a summer school is about. But anyway, so we want to create systems and that exhibit interesting adaptive behavior. And of course, maybe the most amazing adaptive behavior is learning and intelligence. So we try to build intelligent systems in order to understand their organizing principles. So in the end, maybe the goal is not the system itself, but the goal is that you have learned something about such a system. So if we study machine learning, maybe it's not so much in order to build a system that in the end ranks ads or something like that, unless you work for the industry, then maybe that's the end goal. But I think for most of us, we do this because we want to understand something about the organizing principles, something about what makes learning work. And currently, the best way to build build intelligent systems seems to be learning and inference. And it's surprising, or it's noteworthy, that we have made substantial progress understanding the organizing principles of this, and that's what this school is about. Now, what is learning? So I will not define it. I just want to show you the range of definitions that are out there. So these are definitions from, I think, psychology and neuroscience. One says learning is the acquisition of knowledge about the world. So that's maybe closer to psychology. And the other one says, although I think Shepard was also a psychologist, so maybe I'm bullshitting. So the other one says learning is an adaptive change of behavior, change in behavior caused by experience. So this is really quite different. And in a sense, maybe we will see this reflected later on in some of the debates in the machine learning community, this kind of dichotomy. So that's a little bit more, you could call it the symbolic approach, knowledge about the world. Whereas this is the more, maybe the connectionist or data-driven approach, which has its own shortcomings. Because if you read this definition, you can ask yourself, well, for instance, if I break my leg and I start limping, is that a form of learning? Because certainly it's an adaptive chain of behavior. I'm trying not to use the leg that I have broken. It has been caused by experience, but it's maybe not what we have in mind. So this is problematic. I'm not going to resolve it. I just want to show you there's a problem out there. So, so I like to think of empirical inference as something slightly more general than learning, and actually as exactly what we are all interested in, because it includes not only learning but also aspects of inference. So we often will deal with data and we think we're good at inference. So for instance, suppose we are scientists and we have measured this kind of data, and now we want to infer what's the underlying law. Then you might say that's easy. It looks like a linear law, so this might be voltage and current, and this is then the Ohm's law. There's a linear relationship, but you could also say, well, it doesn't actually perfectly explain my data, so I would rather have a nonlinear relationship. And in fact, with a nonlinear relationship, I could even explain this kind of data. So this is a thought experiment by Leibniz, who said, what if I take a quill pen and I randomly splash it on a sheet of paper? Will I not always be able to find some mathematical expression that explains these data? So he was asking the question, when do I think that this mathematical expression is actually a law? So when would I be justified to call it a law? And in a sense, that's still at the heart of machine learning theory, this kind of question. And of course, you can take a practical point of view. This is the point of view of a physicist, Rutherford, who said, if your experiment needs statistics, you ought to have done a better experiment. So if you have to do something fancy with your data, you should find other data. And maybe that was, I think we in this room, we don't believe in this because we would be out of our jobs. But maybe at the time this made sense because they didn't have computers, they didn't have machine learning theory as it's developed now, etc. So this is scientific inference. Let's look at a different type of inference that we perform all the time, and that's in perception. So let's look at this example here. So I have some handwritten digits. This used to be the favorite data set of machine learning, the MNIST data set. I don't know, has anyone here in this room ever used the MNIST data set? Well, still quite a few. Has anyone used the XOR problem? Okay, so XOR is dying out. That's good. Gradually. So this is the MNIST data set, and you will all be able to recognize these digits. Not just because I have written it down here. You can read them. It's an easy problem, easy inference problem. Now, how about these images? This is a 9. That's another 9. That's an 8, a 9, etc. So this looks. Maybe you can pick up some regularities, but it looks like a non-trivial problem. Now the difference, of course, is only that I have applied a permutation to the pixels, and it's a fixed permutation, so there's the same information there in these images, but now it suddenly looks difficult. So in some sense, one could argue mathematically the difficulty is the same, but suddenly for us it looks difficult, and probably the reason for this is that actually the other problem is also difficult. It's just that it looks easy to us because we have been trained on this kind of images all our lives. So there are some problems that look difficult, some problems that look easy, but in reality, both of them are actually probably difficult. And there are difficult statistical problems, and some of them look easy because we have seen a lot of statistical data. And in fact, some neuroscientists have said that the brain is nothing but a statistical decision organ. So from that point of view, you're all doing theoretical brain science because you're trying to understand the task that brains are actually built to solve from a certain point of view. So here's a second inference problem in perception, which I quite like. So it's about color perception, and I have to apologize to those of you who don't know all this. Maybe many of you know this. I guess you all know that color perception is non-trivial. There's this spectrum of light, wavelengths, roughly from 400 to 700 nanometers, and we have this idea that different wavelengths correspond to different colors. So what we see, what color we see, is somehow a function of what wavelengths come into our eye. Unfortunately, in reality, it's a lot more complicated. We don't have a sensor that sees the wavelength. We just have sensors that have different sensitivities for different wavelengths. And in addition, what we see is not even a function of what our sensors measure. And that's easy to see with these color after effects. So if you look at this cross for a few seconds, and then I'm going to switch to another image, and you just keep staring at the cross, then you will see a color after effect for a few seconds. Did you notice it? Yes. And now suddenly everything looks gray. And I haven't done anything. I didn't touch my computer, and it's a stationary gray image. So now you see the gray that's there, but before you saw some color that wasn't there. So what you saw, at least for a while, was not just a function of what was out in the world. So it was something more complicated that was going on in your head. And actually, it's a process of inference that's very useful because in reality, what we see is this reflected light from the. So don't think of this artificial projector stimulus, but think of looking at an apple in front of you. If you try to look at this apple, you will see the reflected light, which is a product of the illumination or of the reflectance of the apple. That's a property of the apple itself. And the illumination. So if you look at the apple in the early morning, maybe there's still some red light. The sun is just rising. And around noon, the light is much more blue or white. So the illumination will be very different. The reflectance will be hopefully the same if the apple hasn't changed. And now you want to take a decision whether the apple is ripe and you can eat it. If you were just to measure the reflected light, it would look completely different. But so what we're really interested in from a biological point of view, of course, is to find out things about the world. So whether we can eat the apple or not is a property of the apple. So it should be a function of the reflectance, and it should ideally be independent of the illumination. And a lot of people have thought about this, and in some sense, this is called the color constancy problem. In some sense, it's still not completely solved. But already Helmholtz was thinking about this problem, and he said, well, somehow we have to look at the scene and infer from all the reflected lights. We have to infer the overall illumination and then factor this out to compute the reflectances of objects, and that's what we see as color. And he thought about a number of such problems. He also noticed that the eye is very poor optically, and so poor that he found it amazing that we can see so well. And he was arguing that actually a lot of perception and vision is some kind of inference, unconscious inference, he called it. And this unconscious inference has to use assumptions, has to do certain computations, and you can fool them by looking at optical illusions. So illusions are what you show to highlight certain properties of this inference engine. So for instance, this is an illusion that all these elements are the same size if you were to measure on the screen, but they look different for you because, again, you try to infer some property of the real world. You try to infer the real size of the elephant, and due to this perspective shortening effect, you think this elephant in reality is bigger than the other ones, so you see it as bigger. Or here's another nice example of an optical illusion. This ball appears to be in the goal. But just because you like to see it in the goal, you would like this to be a goal, where in reality it wasn't. Okay, so we've seen several inference problems in science, in perception. So it looked like in science inference would be trivial. That's what Rutherford said. In perception, it's hard, but of course, scientific inference can also be hard. And that's what we are working on, these kind of things. So this is just one example without details, because I think it shows something about the kind of paradigm shift that we are currently in. So this is from bioinformatics, precision recall curve, some classification problem on DNA sequences, or maybe it was mRNA sequences. And the message here is, if you have a large number of training examples, 10 million or maybe even 15 million, you can do pretty well on this classification problem. But if you only have a few hundred or 1,000, you are very poor, probably basically at chance level. So this is a kind of regularity. Even if I give you labeled data and you look at it as a human and you see a lot of examples of these splice sites and things like that, you won't be able to tell what makes a splice site. So it's a kind of regularity that we wouldn't have seen at all just by looking at the data, but by using machine learning, we can see it. So that's I find that quite surprising, because if we think of machine learning as an approach to artificial intelligence, this means there are some problems where artificial intelligence is in some sense stronger than human intelligence. So this has, in some sense, happened. We're still around. Nothing bad has happened. The robots haven't taken over. But in certain domains, this is already a reality. And it's going to change the world one way or another. So these problems that one could call hard inference problems have a number of properties. They are fairly high dimensional. You have to consider a lot of factors simultaneously. They are complex. They could be nonlinear, non-stationary, etc. We have relatively little prior knowledge, so we don't have a detailed mechanistic model for the data. And of course, as a consequence of these 3 points, we usually need data sets. So if we have all this trouble, we need a lot of data to compensate for it. And of course, to process these data sets requires computers and automatic inference methods, etc. So from that point of view, maybe it made sense that Rutherford wasn't interested in this kind of stuff yet. Okay. So just a few thoughts about one of the core problems of machine learning, this problem of generalization. So suppose we observe this number sequence 1, 2, 4, 7. You can ask what. So this is actually, this slide is based on a lecture that Olivier Bousquet gave here at the summer school when he was still around in Tübingen on learning theory. So I'm not going to lecture on learning theory now, but I think this is so nice. I want to show you this example. So suppose you see this sequence here. What's the next number? 11? Anyone for 12? Or 13? Be courageous. Everything is allowed. Everything is possible, actually. Okay, so 11 is a good solution. It's called the lazy caterer sequence because if you have a piece of cake, then this sequence element tells you how many pieces you can create by n cuts, if this is the nth position, or n minus 1 or something like this. So the first cut creates 2 pieces, the second cut, if it intersects with the first cut, it creates 4 pieces, etc. Because every time the number of additional pieces you create is equal to the number of previous lines you're intersecting, because each of them is sort of, you're kind of doubling, or you kind of, creating one more. So easy problem, you can think about it some other time. Don't get stuck on this now. So 12 is also fine. It's a very simple law. 13 is actually a good one. It's called the Fibonacci sequence. Each digit is the sum of the previous 3. You don't have a lot of evidence for this because only this one is really a sum of 3. But if you continue it would be 13. 14 is another option. So in this case, it's 14, then 28, then the sequence stops because it's the set of divisors of 28. This is another one. It's the decimal expansions of pi and e interleaved. So that was Olivier's. If you're a mathematician, maybe you like this solution. So the next digit should be 1. And if you go to this website, you can enter this sequence here, and then you get all the meaningful continuations. So you get those. I don't think you get this one here. Maybe someone should submit it. And you get 600 hits. So there's a lot of ways to continue this. And then, of course, the question is, which of these continuations is correct? So which of these continuations generalizes? If we were to continue observing the sequence, would we be right or wrong? And of course, the way I presented this, you will all agree that there's really no way to tell. So this is what philosophers call the induction problem, essentially. And it's something that maybe psychologists happily ignore when they construct IQ tests. But from our point of view in machine learning, this is a big problem. And we don't know what to do about it. So how can we use the observed data to come up with a law that's correct? And this is also it's a problem that in particular Karl Popper has thought about a lot. He attributed this the discussion of this problem to Kant. He called it Kant's demarcation problem, and it's essentially the question what separates physics from metaphysics. So what kind of procedures do you have to follow to produce scientific knowledge as opposed to metaphysics? Now we can't solve that problem, but we can solve a slightly easier problem in statistical learning theory. And it's easier because the question is different, and the question here is how do we come up with laws that generalize? So what kind of procedures do we have to follow, actually? So I should say this is the demarcation problem. I forgot to move on. And the answer, in this sense, a little bit more precisely, which is a law that would probably do almost as well in the future as it has done in the past. And in this sense, we can actually answer the question. So that's a slightly easier problem, but I think I'm not going to lecture about this today, but I think we have a course about statistical learning theory, and you will understand in which sense this question can be answered. Okay, so I will switch gears now and move to a little bit of thoughts about the development of machine learning and about the history of machine learning. And of course, if you have to prepare a talk about this, the first thing is you Google, look, history of machine learning. Has someone done the work already? And I found this beautiful plot here on a website called About Data Mining. So this is the history of machine learning according to the data mining field. So we started with neural nets, at some point decision trees, SVMs, and then logistic regression. So this is, I think most of you maybe disagree with this history. But I show this just to illustrate that history is highly subjective. So this is the data mining point of view. It's the history in as far as they consider it relevant for data mining. Maybe these are the main methods used in data mining. And I don't share this view, but I find it interesting anyway. So my view will be a little bit, will have a different bias, will also be biased. It will be more biased towards the machine learning, neural net, pattern recognition point of view. And I, of course, found a number of things that are kind of related to this discussion. Particularly, I found this very interesting paper by a sociologist called Olazarán, I think, from Spain. It's actually a very interesting story. I mean, I was going to talk also a lot more about other aspects of what is machine learning, but I kind of got stuck in this history, and then I ended up having enough material anyway, and I thought this is interesting and everybody should know a little bit about it. So I ended up preparing a lot about this. So where does the history start? Of course, it starts with the old philosophers, Aristotle, Leibniz, etc. But I already mentioned Leibniz before, so I don't have to go so far back. Instead, I'll go to the intellectual background at the time when machine learning, or when people started to talk about this in these kind of terms, so when it was born. And this is the time of cybernetics. Maybe the leading figure of cybernetics was Norbert Wiener. He was born in America. His father was a professor for Slavic languages at Harvard, and Wiener was also a prodigy, a childhood prodigy. He could do all sorts of things early on. He was very fast with picking up languages, was very much interested in languages. When he was 11, he started studying mathematics at college. And 3 years later, he finished his, I guess, bachelor's, and he went to Harvard to study zoology. And then he changed to philosophy at Cornell, returned to Harvard and finished his PhD, I think at the age of 17 or something like that, on mathematical logics. So somehow he got interested in these problems of cybernetics. I think during World War II, when he was interested in this problem of you have one pilot following another one, and somehow how do you control a plane, or how do you predict how the pilot in the front will behave, or something like that. So this kind of questions. So maybe in the end, a military question. And got interested in these kind of control problems. And I think maybe the new thing about cybernetics when it happened was that people said, let's think about what happens to information rather than energy. So is there something interesting going on as we look how information is being processed and communicated? That was probably new at that point of view, and at that point in time, and in a sense it's still what's at the core of what we are still doing nowadays. I think that was quite a profound change. And there was this set of conferences called the Macy conferences. Initial title was Circular Causal and Feedback Mechanisms in Biological Social Sciences, and these conferences are sometimes thought of as the birth of cybernetics and of cognitive science. So there were a number of interesting people associated with this movement. Also the mathematician John von Neumann, Alan Turing, Claude Shannon, and there's a lot of stuff out there to read about. For instance, this is so Warren McCulloch was another one associated with this movement. This is these are his notes when he organized the conference in '53, and it's interesting if you look at all these names. Of course, these are all famous people, and for instance, Claude Shannon here only appears as an alternate down here. And then there were some guys, Turing and Piaget, said no. I think they decided not to come. Actually, for Turing, we even have the letter. He writes to McCulloch. So, dear McCulloch, I like that already. This start, and he says, if it were in Europe, I should certainly try to make it, but I am really rather a stay-at-home type. So that's a nice letter. And so this movement of cybernetics was very broad, influenced by all sorts of fields, and they were also trying to apply it everywhere. For instance, they were trying to apply it to homeopathic medicine, to theology. It made it into the women's magazines of the times. So this one, it starts. Well, it's a little hard to write. It says something like, "What what a modern woman has to know about cybernetics," and they were looking for this process of communication and control in all sorts of systems. So they were. So this is like a spacecraft. This was the time when people were preparing the Apollo mission. This is a control loop in this monkey trying to reach the bananas. Here we have control loops in how we control our breathing, depending on, I don't know, the blood oxygenation or whatever. This is a control loop in preparing food, and people were also thinking about government. So people were thinking maybe we can. We have this bottleneck of electing people who then make laws and take decisions. Maybe we can cut them out of the loop, and we can somehow have a direct feedback loop from the voters by somehow directly having this kind of cybernetic. It was called cybernetic direct democracy. This is a room that's not from a science fiction movie, but it was actually built in Chile by the Allende government with the cyberneticist Stafford Beer. This was kind of the control room used to manage, or it was supposed to manage Chile's economy. So it was only used for a short time because then, of course, Allende was overthrown. But people were quite optimistic in those days about technology, I guess. And it was also the time when this time of the Whole Earth Catalog. I don't know if anyone has read the biography of Bill Gates, this kind of precursor to the internet, and it was like a mixture of technology and I don't know, punk culture, we would call it nowadays maybe, that was born in some sense from this cybernetics movement. Very interesting time. There was people were starting to get interested, of course, in information processing in the brain. Now that they think about information processing, and this is from McCulloch and Pitts, who showed that. So they came up with this model of a simple neuron, and were thinking of it as a little elementary logical processor, and showed that you can compute any logical function by composing such neurons. So I think also the term neural nets comes from that time. McCulloch Pitts had these formal neurons. There was Donald Hebb, a psychologist, who was thinking about how the strengths of connections in such networks could be changed. He came up with this thing called the Hebb rule that was important for a lot of neural network models. And a lot of other things like that. So that was the intellectual climate of that time. And then there was this breakthrough, one could say, which was building on all these things. So that's a list of references from one of the first papers of Frank Rosenblatt. And Rosenblatt came up with this thing called the perceptron. And here we see Rosenblatt with the perceptron, or part of it. This is the retina of his perceptron. So the perceptron is a physical machine, a simple neural network model. And Rosenblatt was apparently a very interesting and colorful character. He was born in New York. I think he studied psychology. He went to Cornell, where he then built this perceptron, and it was probably, it's not completely clear, but probably was the first computer that could learn by trial and error. So by having, whenever it did an error, it got some kind of negative signal, and the weights were adjusted using this kind of neural network built in. So this was an interesting guy. He taught a course at Cornell which was entitled Theory of Brain Mechanisms, but that apparently was a mix of all sorts of different things, with students from engineering, liberal arts, etc. He was talking about brain surgery, epilepsy, neurons, etc. So this was interesting time. And apparently he was a very good communicator and convinced a lot of people to use this kind of perceptron, even to the point where some people got a bit annoyed. So Minsky Paper later write, this perceptron schemes quickly took root, and soon there were perhaps as many as 100 groups, large and small, experimenting with the model, either as a learning machine or in the guise of adaptive, etc., networks. So there were a lot of groups. Maybe some of the major ones were the ones of Widrow and Rosen. And I think this development certainly started in America. And the first, or I'm not sure it was the first one, but one of these perceptrons built by Rosenblatt had 8 inputs. So and 8 outputs. So these are the output units. So only 3 are shown, but it had 8. This was the inputs, what they call the retina, what you saw in this picture before. I think this is the retina. These were fixed connections from the inputs to these so-called association units. And each association unit only was looking at 6 of these input pixels. And they call this the order of the perceptron. So that becomes important later. And these output connections, these were the modifiable connections. From the association units to the output units. So that was the revolutionary thing about the perceptron, that there were these modifiable connections that were learned from an error signal computed on the data. In some sense, this was the first occurrence of what we now call empirical risk minimization or training error minimization in machine learning, and maybe even in the world, because of course statistics existed already for a long time, but statistics was dominated by things like maximum likelihood, etc. So this was quite an interesting development here. And then the shocking thing was that someone came and was able to prove a convergence theorem for this thing. And there's some argument about who did that first. Probably was a guy called Novikov, a Russian name, but working in America. But Rosenblatt had his own version of this convergence theorem, published around the same time, I think. And this is the version copied from the book of Minsky Papers. We will get back to that later. And I don't go into details on this, but basically this says you have some training set, and if this training set of positive and negative points, if this training set is separable, then the perceptron algorithm that just goes through the training set, and whenever you make an error, you add, essentially you add the example, depends how you write it, on which you made an error, then this algorithm will converge a finite number of steps. So if it's a finite training set, you cycle through the training set, at some point suddenly there are no more corrections. You have correctly separated the training set. And surprisingly, actually, you can also write this, if you write it in modern notation, it's this result heavily relies, or it very much depends on the margin of separation that's possible between the two sets, etc. So it's actually really a precursor of a lot of learning theory that we know nowadays. And I think, also from discussing with Vladimir Vapnik, who was in Russia at the time, this result really made a big, was a big shock for people interested, because they suddenly noticed, I mean, for us, this is clear now that we can use mathematics to analyze learning, but I think this was the first really convincing example that this is like a scientific field where you can actually make actual progress, improve theorems, etc. So people were amazed about this. Of course, the perceptron also had certain shortcomings, and people were also well aware of that, and a particular task that could not be learned was this XOR problem. So this it's clear to you. So if you think about different logical conjunctions, AND is easy to learn. Like if this is on and this is on, and you have 2 weights of 1, and let's say so the outputs, it's also important, these units were threshold units, so they just summed up this linear combination of the inputs with these weights, and then checked whether the sum is bigger than some threshold. So if you put a threshold of 1.5 here, then of course, if both these inputs are set to 1, multiplied by 1, the sum is 2, it's bigger than 1.5, the output is 1. But if only one of them were set, then the output would be 1, so it would be below threshold. So this computes the AND function. But it's easy to see you cannot compute XOR like that. people noticed that if you want to compute XOR, you have to make it a bit more complicated. You need additional layers. You need this additional neuron. So for instance, this neuron then would check are both of them on, and if both of them are on, it gives a very strong negative signal to this one. So therefore, if only one of them is on, you're above threshold, but if both of them are on, you get this very negative signal in the middle, you're below threshold. So that's an XOR gate. And of course, also Rosenblatt, the main person doing perceptrons, was aware of these limitations and a number of other limitations, such as the excessive learning time. Of course, you have to think of this perceptron as a physical device. It had around 500 weights that were modifiable, and they were implemented using potentiometers of considerable sizes. So that was not something digital. And actually, I think they didn't want to use digital computers for that because they felt that somehow digital computers doesn't fit together with this brain style of computation. So he built this thing. It was very big. It filled a whole laboratory room. It took a very long time to learn. And he noticed that certain problems are difficult. So there's this kind of problem, figure-ground separation. Or maybe I should also say, so why is this perceptron problem important? Why are people so obsessed? I only understood this while reading about this. So essentially, if you have suppose you have a retina with just 2 pixels, then the perceptron problem is that you want to recognize these 2 things as positive examples and the rest as negative. So in a sense, it's like you want to recognize this very simple object that has just 1 pixel, but you want to recognize it independent of where it is on the retina. And of course, in pattern recognition, you want to be able to do this kind of invariant recognition. So in a sense, the XOR problem, you could say, is the core of, if you can't solve the XOR problem, you cannot hope to get invariant recognition systems. So that's where this obsession comes from. And it's also related to this figure-ground separation problem that he found is hard, recognition of topological relationships, abstract concepts. He was aware that multi-layer systems are hard to train. And of course, there were all sorts of technological problems. Yeah. Okay. So he was funded by the ONR, the Office of Naval Research, and he was a good communicator, made a big fuss out of the whole thing. He made press conferences, and the New York Times was writing after one of these press conferences, just an example, the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Later, perceptrons will be able to recognize people and call out their names and instantly translate speech in one language to speech in writing in another language. It was predicted. So I find it very interesting to read these predictions from the past. And I think some people, or very clearly, some people got very annoyed with this kind of publicity. And Hecht Nielsen, a neural network guy, later remembered about the campaign. He said the campaign was waged by means of personal persuasion by Minsky and Paper and their allies, as well as by limited circulation of an unpublished technical manuscript, which was later de-venomized and after further refinement expansion published in this book, Perceptrons. So this book, Perceptrons, you probably all have heard about that. So we'll talk about this a little bit now. So this was a big debate, and people also remember that Rosenblatt and Minsky had a lot of arguments during conferences, and the people were always interested. Probably was quite entertaining, these kind of debates at the time. So then the so-called XOR affair came with this book. So they published this book. Eventually, that was the thing that was first just circulated. It's called Perceptrons. And in this book, there's just a few quotations from the book. Thank you. A few quotations. So they say perceptrons have been publicized as learning machines, discussed in a large number of books. Most of this writing is without scientific value. And probably that's true. Maybe a lot of bullshit was written about that. And so their mission was to dispel what we feared to be the first shadows of a holistic or gestalt misconception that would threaten to haunt the fields of engineering and artificial intelligence. So they thought that something bad is going to happen. We have to do something about this. Maybe a crucial part is they were analyzing a relatively limited setup. I'll say a bit more about this in a minute, but then they were trying to make conclusions also about more realistic, bigger perceptrons. So they were analyzing the one-layered system, but then they said that it's an important problem to look at the multi-layered setups, but their judgment, their intuitive judgment is that the extension is sterile, so it doesn't make sense to continue in this direction. And it's also interesting to read what Minsky Papers write themselves later on about this. So they were saying that after Rosenbart's work, there were maybe thousands of projects. So before it was still hundreds, but now thousands in the recollection. But they felt that nothing happened. The machines were very limited. People were getting worried. They were trying to get money to build bigger machines, but they didn't seem to be going anywhere. And then they decided they have to do something about it. And this is what Minsky remembers. Papert remembers that there was some hostility in the energy behind the research reported in Perceptrons. And part of the drive came from the fact that a lot of funding was being dissipated on what they thought was misleading and something that's not going to be useful in practical applications, especially. So I find that curious. Now, technically, it's actually an interesting book. But it's not easy reading. It's quite mathematical, and I don't want to say I have read the whole thing. I have read some of it, and I don't want to report it in detail. So this is a figure from that book, and I show this figure because it's important to justify one of the assumptions that they were making. It was some kind of locality assumption. So they did have this. Maybe it was missing. I said before, one layer. Depends how you define it. They did have this first fixed layer, so in that sense it was two layers. But what was important for them, so these weights were fixed, these weights were modifiable. What was important for them is this parallelism here. So people were thinking about parallel computation, the connectionists. And Minsky Paper made this assumption that each of these neurons here, I guess, I can point here, they have a video. Each of these neurons here only has some kind of local input that takes a certain number of inputs. This was the order. And then the question is, with this kind of local inputs, what kind of functions can you compute globally? And it turns out that this problem of parity, which is a generalization of XOR, you could not solve the parity problem unless you make these local neurons have an order which is the whole image. I guess it's maybe kind of intuitive. And they could show similar things for figure ground, separation, connectedness, etc. And then they point out, very surprised, that we noticed that all of these problems can be solved very easily using simple serial algorithms. So that was what they thought was a big blow. And just to show the importance of these problems, parity. So if you look at this image, for instance, I give you 5 seconds. Can you work out the parity of this? So can you count how many black dots are there? Is it an even or an odd number? I don't know, I haven't checked. So this is the other problem, connectedness. Is this one connected black thing or are there two things? Okay, you have a serial computer built into your brain. Yeah. Okay, you were using logics. That's also serial stuff. So the connectionists felt that, okay, we can't solve this, but maybe it's not so important because humans also cannot solve that. But the discussion was not so clear. And the book actually got a pretty positive reception. So for instance, so here's some examples. Well, maybe first this one. This was written by Alan Newell, a long review of the book that was published in Science, and the review starts with the words, "This is a great book." And then at the end of his long review, he says, "I should remark perhaps that I'm not an unbiased witness. For I share with Minsky Paper the common view that the appropriate shaping of computer science," so this was also the birth of this discipline of computer science. So he shares this view of how the field should be shaped, and I see no need to give other than my true, etc. Yeah, so this was also, in some sense, maybe a political issue. It's related to these Gestalt things that we talked about before. Computer science was being created, and they wanted to make it like a clean mathematical discipline. That's my impression from reading these things. This is a slightly different review written by Bloch, who was in Cornell, so I assume he was closer to the perceptron guys, Rosenblatt, who points out that another indication of the difference in perspective is this concern with predicates such as parity and connectedness, and he points out humans cannot perceive this, so maybe it's not so important. So now the official history is, and probably you've read this in textbooks, etc., that the book Perceptrons, this is the book, killed perceptrons in a sense, or put an end to neural networks by showing that perceptrons could not learn the XOR problem. Right? Is that what people believe? I think so. At least I used to believe that. And actually, it's kind of surprising that until recently it was still common practice that people would feel the need to show, if they develop some new method, they had to show that it solves the XOR problem. It was, I still remember reviewing lots of papers like that where the first problem they solve is the XOR problem. So we have this obsession with the XOR problem that comes from there, I think. And there's a slightly more sophisticated version of the history that says that this book actually didn't completely show that perceptrons didn't make sense. It just showed that one-layer networks didn't make sense because they can't learn the XOR problem. And also, people didn't know how to train multi-layer systems, and therefore, sort of neural networks were stalled for a while, and that killed them. And probably both accounts are more or less wrong. That's what's interesting about this story. So it's quite clear that people who were technically in that field didn't think that this book kills perceptrons. They thought that it was very restrictive what they did. So for instance here Bernhard Wiener said, when I first saw the book I came to the conclusion that they had defined the idea of a perceptron sufficiently narrowly so that they could prove that it couldn't do anything. So people were well aware that this was very, very specialized and the negative results only applied to that case. So that's one quotation, and also one should say that Rosenblatt and others were already using extensions. They were already using networks that had two layers of modifiable weights. They were using things like feedback connections within layers. They claimed that these things worked better, but of course, if the original perceptron was black magic, this was even worse. Nobody understood what's going on. So then the interesting question is, what did actually end the perceptron? And this is discussed in detail by this sociologist. I think he wrote his PhD thesis about this in Edinburgh. So one interesting thing he points out is what seems to be called the arithmetic ideal in science. So Minsky and Paper they were both serious mathematicians. They had PhDs in math from Princeton and Cambridge. If you look at their book, it's serious mathematics. Bloch points out all sorts of mistakes in his review, but overall, this is a serious mathematical book, reasonably advanced. If you compare this kind of book to how the Rosenblatt articles are written, it's a big difference in style. So if it's clear that if Minsky and Paper were to submit an IPS paper and Rosenblatt, then Rosenblatt would be rejected and Minsky and Paper would get in, just by scaring the reviewers with their mathematics. So this looks like serious science, the way they presented their work. And I think they also had this hope that they can defend their field against this Gestalt principles and what they perceived as non-scientific. So that's interesting also if we think about it from our current point of view. Of course, Rosenblatt had the big original idea. The breakthrough came from Rosenblatt, but he sold it in a way that maybe nowadays wouldn't get into NIPS. Maybe that should give us something to think about. But there's maybe a stronger reason, according to Olataran, which was that one has to think of this as a competition between different fields. And there was this competing paradigm, symbolic AI, that was gaining momentum at the time. So digital computers became available. People started to develop high-level programming languages. And many of them actually developed by symbolic AI people. So for instance, I think Minsky developed Lisp, if I remember correctly, and one of them developed IPL, etc. There were also some early successes of symbolic AI. There was something called the general problem solver. There was a logic theorist trying to prove logical theorem. There was something called student that had some kind of simple English language interface, which led Minsky to proclaim that student understands English. There were initial successes with chess systems, etc. So people started moving to this competing paradigm. Also, Rosenblatt died very soon in a boating accident in '71, and somehow ARPA, which is now called DARPA in America, this Defense Advanced Research Projects Agency, decided to cut off funding for neural networks and decided to back symbolic AI. And in some sense, this was very important for the start of symbolic AI because it helped legitimize it as a field. So this, which maybe is clear from this quotation from Newell and Simon, two of the important people of symbolic AI. They said the principal body of evidence for the symbolic hypothesis is negative evidence, the absence of specific competing hypotheses as to how intelligent activity might be accomplished. So in a sense, one could even say it was important that this other field was killed because this was the competing hypothesis. So what was, so it's overall, I think it's, one can think about these early successes of AI, symbolic AI. We all know that symbolic AI later on had a hard time. And that a lot of these things, in some sense, went nowhere. And in retrospect, I guess one can say that many of these early successes were really not successes of symbolic AI, but they were successes of the advent of digital computers, because they could suddenly do a lot of things that previous generations couldn't do. It's again, I think, something that we can relate to current times, that we should be aware of, that we think we are doing amazing things now with machine learning, but maybe some of these things we can just do because we have much bigger computers and bigger databases and data sets, storage, etc. So it's difficult to attribute the credit to what really makes the breakthrough work. So I think a lot of these successes were really due to computers being around for the first time. So symbolic AI was probably very limited, but it worked together well with computers. So it was the right time for symbolic AI. And maybe that's what killed neural networks. So what was symbolic AI about? So maybe in one sentence, the paradigm says that intelligence is a process of manipulating discrete symbols. And there was this set of summer schools that started the field. People also, I think, came up with this name, artificial intelligence, after heavy discussions. These were some of the most important people in that field. And one could argue, or some people argue, that symbolic AI is actually what helped to transform computers. So people claim that computers initially were just like calculators, computing with numbers. People argue that symbolic AI helped to transform this into this more general view of a computer as a system that processes symbols. But that's probably not true, because apparently already Zuse, who developed the first programmable computer in Germany, was aware of this and was already envisioning, for instance, chess-playing computers, as that's what he said later on. He just said he didn't dare to talk about this only to his co-workers, but not in public, because he thought people would think this is crazy. So symbolic AI, of course, was controversial too, in some sense already at the time. So in this sense, it was actually important that it held its ground against connectionists. And there was this thing which I think is also quite interesting, so I recommend, if you have time, to look at it sometime, the so-called Dreyfus affair of AI. So there was this, I think, famous talk or paper by Herb Simon. Oh, sorry. Yes, I was. Okay. Thank you. So you should all speak up if something like this happens. There was this famous talk by Herb Simon, who later won a Nobel Prize and I think and the Turing Award. In '57, So this was about this general problem solver. He tried to extrapolate what's going to happen in the future, and he predicted that within 10 years, a computer would be world champion in chess, would discover and prove an important new theorem, would write music of considerable aesthetic value, and also that most theories in psychology would take the form of computer programs. So this was quite courageous. And Hubert Dreyfus and others also, but he was one of the most outspoken critics of this approach, and he wrote this paper called Alchemy and AI, which is actually, you can find it on the web. It's quite worthwhile to read. So in this paper, he's looking at different areas. I think it's game playing, problem solving, so theorem proving, language translation, and pattern recognition. And he goes through these fields one by one, trying to show that no real progress has been made. And but actually it's interesting, he points out that it seems like the first three problems all presuppose progress in pattern recognition. So I think he kind of recognized that this is important to continue in this direction. So I have to speed up a little bit here. So anyway, perceptrons were killed, and in some sense this started this exile of machine learning, or at least this kind of machine learning. Only a few groups continued, most of them outside of America. Hinton was in England. Grossberg was in America, though, but he's kind of a very independent guy. But of course, also in this time, very interesting things happened. So Wapnik Jermeninkis and other people in Russia, in this institute of the Russian Academy of Science, the Control Theory Institute, they heard about the perceptron and about the convergence theorem. They were amazed. A lot of people started working on this stuff. And this, in a sense, started statistical learning theory. So statistical learning theory was developed in these maybe 15 years from 68, or maybe the mid-60s. Expert systems were the big thing of symbolic AI. But of course, people noticed there are limitations to expert systems. And then starting from expert systems, they were starting to make them probabilistic. And Judea Pearl was a major person in this direction. He wrote this big book, Probabilistic Reasoning in Intelligent Systems. And this essentially gave birth to what we now call Bayesian nets. So a lot of interesting things happened. And of course, neural networks came back at some point. People noticed that symbolic AI had its problems. It was good at chess, but very bad at a lot of other things. Computing became a commodity, where, I mean, before there were the top symbolic AI labs, such as the MIT AI lab. They had computers, and other people didn't have computers. It was too expensive. They didn't have funding. But now suddenly computing became a commodity. And then there was this parallel distributed processing group formed by psychologists. So this didn't come from inside computer science, but people from outside noticed it's time to look at these things again. Rumelhart, McClelland, physicists moved into the field, in particular John Hopfield, who sort of compared certain neural networks to Ising models. Hopfield was very influential for the field. He also brought other field people into, I mean, he was a PhD advisor of a lot of people, for instance, David Mackay, Sam Roweiss, and others. The Boltzmann machine was developed, in some sense, the first multi-layer approach for learning, a stochastic approach. And then, of course, backpropagation was found, or invented or reinvented. Around the mid-1980s by a number of people. That, of course, then triggered Minsky Paper to have a second edition of their book. They felt they have to react to this, or maybe the publishers felt we can sell a lot of copies now again. And in this book they're writing, we have the impression that many people do not understand that this backpropagation is merely a particular way to compute a gradient. And have assumed instead that backpropagation is a new learning scheme that somehow gets around the basic limitations of hill climbing. So they thought hill climbing is just not the way to do AI. And actually, I find this quite interesting. They say little good can come from statements that blah, 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 as a practical matter leads to solutions in virtually every case. Or GD, I think this is the generalized delta rule. So that's backpropagation essentially. Can in principle learn arbitrary functions. This is not just technically wrong, but it's also it deflects us from real valuable insights or science. So they were apparently still annoyed about this. It's interesting to think about why backpropagation was not invented earlier. Why did Rosenblatt not invent it? After all, it's relatively easy. I mean, it's just simple calculus. There are different answers to this. One is, of course, that Rosenblatt was using discontinuous activation functions. He had these threshold functions. They needed to be replaced by smooth functions that you can compute the gradient of. You can then ask, why did people not do that earlier? Maybe the other answer is similar to what I said before. In some sense, maybe the field wasn't ready for it yet. And maybe that answer is supported by the fact that actually Welbosch had invented it already earlier, but it was kind of ignored. So then it was invented for the field when the field needed it, and that was in the mid-80s. Okay, so there's a lot of things that I didn't talk about and that I also didn't prepare so well, so maybe it doesn't matter if time is running out now. Of course, a lot of influences that we have in machine learning come from probability and statistics. And that can be traced back very early to Bayes, Laplace, for instance. It can be traced back to Gauss' method of least squares. It's really also a very interesting person to look at is Ray Solomonoff, who died just a few years ago, who was very early in bringing probability into AI. There was development of MCMC method. There was the PAC community in America that probably approximately correct. It was like the American style of learning theory, building on the VC theory, but they somehow felt that VC theory is this Russian thing developed by this strange, I mean, maybe I'm not doing justice to them, but developed by these strange control theorists in Russia. And PAC had a slightly different focus maybe, and they were also more, they were also more interested not just in statistical complexity, but also in computational complexity. But that was also a major development in America. The conferences started, UAI, specifically with the word uncertainty in their title. So people notice in the AI field they need probabilities. There was the first NIPS conference just after this development of backpropagation. People started to develop probabilistic foundations for machine learning, and there's a number of people in this that should be in this list, and haven't thought about it enough to write this list. And also one should say it's impossible to write history for things that are so recent. SVMs happened, so a lot of interesting things happened. Now SVMs, of course, I could say a lot more about. So in some sense, the two ideas were already around for a long time that people put together for SVMs. Wapnick had proposed this generalized portrait algorithm as a modification of the perceptron method, you could say, a modification that has better statistical properties. Already in the 60s, kernels had been around since early 20th century. They had been around in statistics also for a long time. They had been actually kind of dismissed in this early pattern recognition book by Duda and Hart as being appealing for their mathematical beauty, but not practically useful. So it's another interesting curiosity. So actually, this is a nice picture of Vladimir Wapnick. So the fascinating thing, so I said history is impossible to write for such young things, but the fascinating thing about our field is that it's still so young. So sometimes we can experience major developments as they happen, and probably you will all experience such developments in the next decades, and possibly even things that will become part of what would be called the history of our field. But of course, that will be judged later on. So it's so from my personal experience, for me, it was very interesting to experience some of the history of kernel methods and support vector machines. So maybe I should spend the last 5 minutes or a few minutes saying a little bit about this. So I got into this field in 1994. And I was looking the other day, and I found the first email that I got from Vladimir Wapnick. I thought I had lost it, but I found it, so I was quite happy about it. I've never showed it to anyone. I will just briefly show it. And this is so 1994, and he said, I like that you study philosophy and math. There's a story about this that I can tell you over a beer sometime. And he says, we discuss questions that was discussed in philosophy. And down here he says, we also found a way to control the generalization ability of learning machines acting in very high-dimensional space, say in space of billions parameters. And we hope that these types of machines will do better than neural nets. And then, so I came to Bell Labs and started working with Vladimir. Actually, also one thing that I found curious, I had sent him, I wanted to go there for half a year to visit. So I told him, look, I want to visit for half a year, do something interesting, and then go back to Germany, do a PhD. But he completely ignored that, because in his email down here, he says, in Bell Labs, you will study my new book. And then, wait, and then, oh yeah, after this study or during it, we will decide what can be theme of your thesis. So sometimes it's good if someone tells you this is the anyway, so I got involved in this stuff, but actually my first job was to train a neural network. I had already worked on neural networks a bit before, and then I had to train the neural networks for this first book on SVMs, the Cortez-Vapnik, first article that used the name support vector networks at the time. So this was by Corina Cortez and Vladimir Vapnik, and they needed a comparison. They wanted to show that they're better than neural nets, so I had to train the neural network. It was pronounced the best two-layer neural network. This was my number, and then a number of interesting things happened in this kernel field. It was pointed out that one could do this kernel trick for arbitrary dot product algorithms, and also that it doesn't require vectorial data. It can be, in principle, also defined on other kinds of data, etc. But I should get to my conclusions. And the conclusions are of the most difficult part, and I spent the least time on them. So where is machine learning heading? That's probably the big question that we all want to know, and predictions are difficult, especially about the future. We all know this from Niels Bohr. So I don't want to predict too much, but because it's invariably going to be embarrassing if someone looks at it later on. We see a lot of technical issues in machine learning currently that people are interested in. Issues related to optimization, structured data, efficient learning and inference, sparsity, etc. That's certainly going to continue for a while. I think that's a safe prediction. Another safe prediction you can always say is that people will have to think more about how to integrate prior knowledge and domain knowledge. That's just such a difficult problem. It's not going to be solved easily. I found this actually as, in some sense, also in predictions that people made 50 years ago. So I'll predict it again, and I think that's going to happen. We don't have a very good handle on how to learn control and reinforcement learning compared to how we understand other types of learning. This still seems to be quite broken, and it's a very important problem. We think, and that's also one thing that we're interested in at this institute, we have two branches, and one of them is more into hardware. We think that learning in physical systems will also be an interesting topic, synthetic or hybrid physical systems. It will be interesting to think about learning in settings that don't satisfy our usual assumptions, because in real life they're usually not satisfied. So in real life we learn in environments that are populated by other agents, rational or irrational agents. And this of course means that we have to link up things much better with game theory, and we have to develop game theory. It's also a field that's not that far developed. And of course, I think non-stationary settings will be very important. And personally, I think this is very much related to causal learning, and you will hear more about this at the end of this week. So I think that's also an important direction to go in. Now, actually, the title of the talk was, "What is machine learning?" I haven't answered that yet, you might point out. There's different ways of answering this. One is it's not statistics. I put that in inverted commas because it refers to a story that Vladimir Vapnik once told me about when they came up with their first results about VC dimension and this combinatorial parameter determining the generalization ability of machine learning. They tried to submit, they thought they have something big. They noticed that immediately they wanted to publish it in the Proceedings of the Russian Academy of Science. To do that, you had to talk to an academician and get his sort of approval or endorsement. And they talked to, I think they talked to Gnedenko, and he looked at it and he said, well, that looks very good, but I'm sorry, we can't publish that. It's not statistics. He was somehow for the statistics section. And they said, well, why is it not statistics? It's a generalization of the Glivenko-Cantelli theorem. It's a major theorem of statistics. And he said, no, statistics is not defined like this. Statistics is what I'm doing, what my students are doing, what these guys are doing. So in that sense, there's this cultural definition of fields. So what is it not? It's that machine learning is still a young discipline. We talked about that. I think that's fascinating because most of our heroes are still around. And although, as I pointed out before, it's too early to write history, and history anyway should be done by professionals, historians. I think there's already a lot to learn from the history. So I think there's a lot to learn from this Perceptron story. I let you draw your own conclusions from that. But if you walk out of this talk thinking that the things that you believe and that you're so sure about now might just be considered completely wrong in 20 years, then that was useful. So thank you very much.
So, without setting a precedent, thank you very much. I think we have 5 minutes maybe for some quick questions.
Or during the break, whatever you prefer.
Yes, and of course, if anyone in the observation lounge has some questions, then this is the time now to say something.
If you ask me historical questions, you will notice that I'm out of my depth very fast. Yes.
You talked about statistics, but you didn't talk about
system identification. Oh.
Okay.
Yes, well, in some sense, you could put that into this area of learning control, certainly related to that. And I agree. That's well, I'm not sure. So if you're saying that should be in there, and that's an important topic to think about, then I agree. Yes.
Lena is trying to combine these two.
Yes.
Topics.
Yes.
How machine learning can affect the system.
Absolutely. Yes. Yeah. So we've also been we have tried to somehow move into this direction and look at some problems that are related to this. I think it's very interesting. It would be, for instance, very interesting to have some kind of learning theory in that domain, because there are these examples that if you have so we are learning functions mostly, right? So one can think about, why don't we learn differential equations? Because in physics, most laws are differential equations. And there are these interesting aspects, like there's this the universal differential equation of Rubel. It's I think I don't know, 7th order or something like that, nonlinear differential equation, for which you can show that every continuous function or every differentiable function can be arbitrarily closely approximated as a solution of this differential equation with suitable side conditions. So in a sense, that's a differential equation with infinite capacity. It's like infinite VC dimension, but there's no learning theory about that. It would be fascinating to work on that. Yeah.
Any other questions in here? Are there any questions from the observation lounge?
Hello?
Yeah?
Can you hear me?
Yes?
Yeah, so people have been talking about big data, and my question is, do you think we need any major change in machine learning to cope with that sort of new paradigm of learning?
Yeah, it's an interesting question. So if you think about it from this historical perspective, maybe for big data, we're in this same situation that symbolic AI was when suddenly computers appeared. They could suddenly do new things. They were very enthusiastic, but it took a long time to really learn how to make use of the new technological developments and what kind of algorithms you use for the new computers that you had, etc. So maybe the change is not as dramatic because we already have computers; they're just getting bigger. But I don't know. You know, history will tell whether we think this was just a gradual transition or suddenly there was so much data that something fundamental changed. So there's also this problematic issue of who owns the data nowadays, because a lot of the data is collected by companies, and if you use Google image search, you type some keywords, you get a set of images, then you click on one and you give Google a labeling of that image, and they get billions of labels like that. So data is becoming more important. We can process huge data sets, but also who owns these data nowadays. So there's a lot of things that to me are not clear where they're heading and what kind of developments will be spawned by big data. So I think I shouldn't speculate too much. Yeah.